This is an introduction to intermolecular forces. And the one message I want to make sure you walk away with is that intermolecular forces are electrostatic attraction between molecules. So you see this is a water molecule, this is a water molecule. The intermolecular forces are in between the various molecules, okay? A covalent bond or ionic bond, actual bond, are within a molecule, okay? So intermolecular forces are weaker than regular chemical bonds. They're still they're still electrostatic attractions, but they're quite a bit weaker than regular bonds. All right, intermolecular forces, we'll abbreviate that IMF, are very important for one reason, because it determines the state of matter that something's in, whether it is a solid, liquid, or gas. Because if you think about the attraction between molecules, see all of these, the stronger the attraction is, the closer the molecules are to each other. So the molecules that make up a solid are extremely close together because their intermolecular attractions are very strong. On the other hand, gases have almost no intermolecular attractions, and therefore the molecules are far apart, and that's what makes them a gas. There are quite a few other physical properties that are affected by the strength or the type of an intermolecular force. But this is a nice summary table. Again, if the intermolecular attractions are weak, it will be a gas, and there'll be a large distance between molecules. Of course, as gases are unique in that they are the only state of matter that are easily compressed, which makes sense because there's so much space between the molecules. Also, a gas will assume whatever shape and volume of container that you have, because they don't have those intermolecular forces holding them together. So make sure you're familiar with the properties on this table. As I said before, solids have the strongest intermolecular attractions. And because of that, there's virtually no space between molecules. And there are two real kind of general categories of solids. We have crystalline solids, where there's a repeating, very orderly arrangement of the molecules. And then an amorphous solid, where there's still quite strong attraction between molecules, but they don't make a repeating regular pattern. They just kind of clump together. So an amorphous solid might be like a piece of metal or silly putty or a rock. And then crystalline solids are things that look like crystals. And that's what makes them so pretty, is that repeating pattern. So table salt, most ionic compounds are crystalline solids. Actually, I think all of them are. And so those are just two major categories of solids. Particles in a liquid, of course, still have strong attraction between the molecules, not quite as strong as a solid. Even though there's a little tiny bit of space between molecules, we still say that liquids are not compressible. However, this little bit of space allows liquid molecules to flow past one another. Okay, and so that's why liquids flow. You can pour a cup of water from one container into another because of those little tiny spaces allow sliding of molecules past one another. And then gases, probably the most interesting from a chemist's point of view. We kind of make the broad assumption that gases have no significant intermolecular attraction. They actually do a little bit. But because of that, particles are very far apart. And because of all this space in between particles, gases are the only state of matter that are compressible. Gases have a lot of unique properties, actually. And this is just being redundant. All right, so as I said before, intermolecular attractions, just like chemical bonds, are electrostatic attractions, okay? Electrostatic simply means you have some development of charge, and of course, opposite charges attract. So for intermolecular attractions, we're going to go over three or four major types of intermolecular attractions, but they're all electrostatic attractions. So, for example, if you're looking at a water molecule, and hopefully you know that is a polar molecule, which simply means it's got some portion of the molecule with a partial positive charge and another portion with a partial negative charge. And because of these partial charge separations on a water molecule, we have a pretty strong intermolecular attraction between two water molecules. And of course, since opposite charges attract, it would be the hydrogen atom on one water molecule with its partial positive charge being attracted to the partial negative charge on the oxygen, which is electronegative, on another molecule. We designate these intermolecular attractions with these dashed lines. Okay, the stronger the attraction, the stronger the intermolecular attraction, the harder it is to separate them, right? And so I want you to start thinking about all the properties that are affected by the strength of intermolecular forces. Mainly, or first thing you should think of is the boiling point or the melting point of a substance. When you have particles, I'm just going to draw little blobs, that are attracted to each other, and you apply energy, let's say heat, thermal energy, what's going to happen? What's going to happen first is these molecules, these particles, are going to start separating from each other. And they're going to start loosening the intermolecular attractions that exist between them. And when the intermolecular attractions loosen enough, it changes state. So if you're starting with a solid material where all the particles are really, really close together and you apply heat, okay, they will spread out, loosen up, the intermolecular attractions will be broken, so to speak, until it becomes a liquid. And then if you continue to apply heat, eventually it will become a gas. It is very important to realize, though, that when you change phases, you do not break any covalent or ionic bonds, okay? When you change phases, you only disrupt intermolecular forces. So, for example, if you have liquid water and you heat it so that it boils, you will get a gas, okay? You'll get water vapor, but it's still H2O. You haven't broken any of the covalent bonds. That's important to realize for a change of phase. So turn off the video for just a minute and see if you can answer this question, and then I'll go over it and you can see if you got it right. So here is a diagram of liquid water. And it says, which of the following diagrams best represents water vapor? So that means if you were to apply heat to the liquid water. Let's look at each example. The actual correct answer is A, because that's the only one that kept the H2O molecules intact. Remember I just said we don't break any covalent bonds when we change phases, that we just spread apart the molecules, we just loosen up the intermolecular attractions. So we completely changed the molecule in B, okay? We've changed it from H2O to, looks like now we have H2 and O2, so that's wrong. We aren't making new molecules. And same thing here. We've broken the H2O molecule into distinct separate atoms, so that does not happen during boiling. All right, so just kind of a reminder, you may have seen this. You're not going to do any calculations with Coulomb's law, but it's really handy just to remember that the force of attraction, any electrostatic attraction, whether it's covalent bond, ionic bond, intermolecular forces, anything, depends directly on the magnitude of the charges, okay, the plus and minus charges, okay, whether it's a partial charge or a full charge or whatever. And then it's inversely proportional to the distance between the two charges. So in order to have a stronger attraction, force of attraction, you want to minimize the distance. So I think it's pretty clear how you can increase the force of attraction with the charges. So a +2 charge, for example, is going to be more strongly attracted to a minus charge than a +1 charge. Okay, so the larger the absolute charge, the stronger the attraction. The distance might be a little trickier to understand. What would affect the distance? Okay, so the smaller the distance, the stronger the attraction, but what would affect the distance? The size, okay, of the particles or atoms that are attracted to each other. If you have a really big atom, let's say iodine, and then a smaller one, and you're comparing the electrostatic attraction between that and then let's say maybe fluorine and hydrogen, the distance between fluorine and hydrogen is much smaller than the distance between the larger atom and iodine. And therefore, the force of attraction for fluorine and hydrogen would be much higher, okay, because they can get closer to each other. All right, so now to the basic categories of intermolecular forces. These are important. The weakest intermolecular attraction is called London dispersion forces. Some people just call them dispersion forces. Every single atom and molecule has London dispersion forces. We call it temporary polarity, and we'll explain what the heck we mean by that. But quickly right now, it's even molecules that are not polar, that do not have a dipole, experience temporary polarity and have London dispersion forces. All right, the moderate, a little bit stronger intermolecular attractions are called dipole-dipole attractions, and any molecule that is polar, has a dipole moment, has dipole-dipole attractions. And then there is the strongest intermolecular force, and that is called hydrogen bonding. Okay, that is down here, hydrogen bonding. And I always say hydrogen bonding is fun, okay, to help me remember that hydrogen bonding occurs with molecules that have a hydrogen directly attached to either a fluorine, an oxygen, or a nitrogen. All right, so let's talk specifically about each of the three intermolecular forces. You need to be able to identify what are the forces that any molecule has, and so this will help you. So go in a little more depth about what I meant about a temporary dipole that is seen in London dispersion forces. Let's look at something like a diatomic, okay? We know a diatomic is nonpolar because the difference in electronegativity is 0, okay? But even diatomics will have temporary dipoles. And what happens are the electrons, this just the plus represents the nucleus. The electrons in a particular atom move around. We don't know exactly how they move, but we know they move. So at any point in time, you may have a very dense area of partial negative charge and then a less dense area, which gives it that section of the atom or molecule a partial positive charge. So for a moment in time, you have an instantaneous dipole, and during that time, there will be very weak intermolecular attractions between that molecule or atom and others. Again, London dispersion forces are present in all molecules. So that's important to remember. That tends to be a standardized exam question. Some molecules have stronger London dispersion forces than other, and it depends on how well the electrons can distort or how free they are to move around an atom. So if you remember when we did periodic trends and ionization energy, how tightly the electrons are held by the nucleus, that affects the strength of the London dispersion forces, okay? And we call that polarizability, okay? So the easier it is for the electrons in an atom or molecule to move around and shift, the more polarizable they are, and the stronger the London dispersion force of attraction will be. So what type of atoms or molecules are polarizable, are more polarizable? It turns out the larger the molecule or the larger the atom, the more polarizable. And that's simply because the valence electrons are farther away from the nucleus. They're more loosely held, and therefore they can be distorted and moved around more easily. So to give you an idea of that, look at all the noble gases, from the very small helium to the very large xenon, and look at the boiling point of xenon versus helium, okay? Now, all of them are gases at room temperature, okay? But we can cool them down to see when they liquefy, and that gives us the boiling point. So the explanation for this is that because xenon is so much larger, its electrons are farther away from the nucleus, therefore less tightly held and more polarizable. Okay, so the larger the atom or molecule, the more polarizable its electrons are, and therefore the higher the London dispersion force of attraction is. Alrighty, we can see that dependence on size in molecules also, and in shape. So if we compared, let's say, pentane, which has 5 carbons, to butane, which has 4 carbons, which one do you predict has the higher boiling point? Okay, it turns out pentane does, higher boiling point, because it's a larger molecule, and it's not just the electrons being more polarizable. A larger molecule has more points of attraction along the backbone, therefore the overall force of attraction with other molecules of its kind are a little bit harder to break apart. And so the other thing, in addition to the overall size, that's molar mass, you also have to look at the shape, okay? It turns out that if you compare a linear, even though it's drawn like this there, but it's still, we call this linear, okay? Doesn't have any branches, and you compare that to a molecule with the same molar mass. So the molecule over here, neopentane, has the same number of carbons, 5 carbons and 12 hydrogens as this one. So the molar mass is the same, but check out the boiling points. The boiling point of the linear one and pentane is 36 degrees Celsius, and the boiling point of neopentane is only 9, okay? So it's much easier for neopentane to boil because it's bulky, okay? Easier to boil, lower boiling point. Bulkiness prevents a real close contact with another neopentane molecule. So bulkiness prevents close contact, and so the intermolecular attractions are weaker and the boiling point's lower. And just kind of to emphasize what we just went over, let's compare same type of makeup, hydrocarbons that contain only hydrogen and carbon, except let's get to a larger and larger molar mass, C5, C6, C7, etc. And check out the boiling points. They actually go up in a linear fashion. So pentane is boiling close to 40, and once we get 9 carbons, it's boiling at about 150. Big change. All right, the moderate intermolecular attraction, called dipole-dipole, is only seen in compounds that have a permanent dipole, in other words, in polar compounds. And so remember, that was not too long ago. You have to, in order to be a polar molecule, you have to have at least one polar bond, and you also have to be, the molecule has to be unsymmetric or asymmetric. So you've got to remember how to draw Lewis structures and shapes and determine symmetry, all right? But the bottom line is, if you have a dipole, if it is a polar compound, it will have a partial positive on one end of the molecule and a partial negative on the other end. And because of that, it has quite a strong attraction to other molecules of its kind. Okay, positive and negative are attracted to each other. So let's compare a polar molecule, okay, to a nonpolar molecule. If you haven't written down or remembered when I have mentioned before that carbon-hydrogen bonds are nonpolar, always. That's an important one to remember. It'll help you throughout chemistry. But the electronegativity in hydrogen and carbon are very similar. And so the electronegativity difference between the two is, I think, only 0.4. So hydrocarbons are always nonpolar molecules. Well, check out the boiling point. Okay, again, these are both gases at room temperature, so that's why they have negative boiling points. But ethane, okay, which is nonpolar, boils way before formaldehyde, okay? And that's because it's nonpolar, and formaldehyde has a polar bond and is not symmetric, so it has dipole-dipole. And look how close their molar masses are, okay? So molar mass being the same, dipole-dipole is much stronger and leads to a much higher boiling point. This is just another diagram to emphasize the same point. So if you compare 5 totally different molecules, okay, so propane, it's a hydrocarbon, so it's essentially nonpolar. That's a very minimal dipole moment. And then the polarity is increasing, going down. The higher the dipole moment, the more polar a molecule. And as polarity goes up, look what happens to boiling point. It also goes up. Okay, so that's kind of cool. All right, the strongest of the 3 types of intermolecular forces is hydrogen bonding. And again, that can only occur when a hydrogen atom is directly bonded to either a nitrogen or a hydrogen or a fluorine. Okay, all other hydrogens attached to any other atom does not end up in hydrogen bonding. Hydrogen bonding is just actually a very strong type of dipole-dipole force, okay? You have to be polar, a molecule has to be polar before it can possibly have hydrogen bonding. Remember now, because you'll probably be shown a diagram and it may say identify the hydrogen bonds. My dog's going to start barking. Remember that the dotted lines represent the hydrogen bonds and the solid lines represent the covalent bonds, okay? So, and remember that the hydrogen bonds occur between an atom or an area of a molecule with a partial positive charge and on another molecule, the area that has a partial negative charge. All right, I love this particular graph because if you look at the last 3 points for all 3 lines, there's nothing real, I mean a little bit of inversion here, but there's nothing real unexpected. They're almost linear. But if you look at these initial points on all of them, there's a huge difference in boiling point. They have roughly the same molar mass, so let's say CH4 is around 16, ammonia is around 17, hydrofluoric acid's around 20, and water is around 18. So they have comparable molar masses, but dramatically different boiling points. So the one with the biggest difference by far is methane, which happens to be natural gas, CH4, has a much, much, much lower boiling point than any of the others. And that's because these top three can hydrogen bond. Okay, so that automatically makes their boiling points way higher than expected. If you look at the second, third, and fourth data points, the molar mass is increasing with every step. But then look at all these. Even though the molar mass of the ones to the right are higher, much higher, the boiling point of these first ones are beat all of them because of the hydrogen bonding. So it has a pretty dramatic effect. So this would be a typical multiple choice type question you might be asked on a test. Identify the type of intermolecular force for each of these two molecules and predict which one would be stronger. So I suggest turning off the video at this point, giving yourself a chance to answer it, and then turn me back on and I'll explain it. All right, so we have to determine polarity, okay? The boron-bromine bond is certainly polar, okay? Bromine's more electronegative, so I'm going to draw the dipole towards bromine. However, as I always say, overall, this molecule is symmetric. Therefore, all the dipoles cancel. It's nonpolar overall, so it does not have dipole-dipole forces. All it has is London dispersion forces. Let's see. And in this particular molecule, I told you that carbon-hydrogen bonds are nonpolar. Their electronegativities are very similar. But we do know that the carbon-oxygen bond is polar, okay? And oxygen-hydrogen bond is polar. So this oxygen is our partial negative portion, and the rest is our partial positive. So this will see a dipole-dipole, and what else will it see? This hydrogen is attached directly to an oxygen, so we will also see hydrogen bonding. And then, of course, all molecules have London dispersion forces. So this this has the higher force of attraction, therefore the higher boiling point. Another property that's affected by the strength of intermolecular forces is solubility. And almost always when we talk about solubility, it will be in water. There is a saying that chemists like to use that like dissolves like. And what that means is that polar compounds will tend to dissolve in polar solvents, and nonpolar compounds will tend to dissolve in nonpolar solvents. A real-life example of that would be oil and water. So if you had water and you dumped in oil, you're going to see two distinct layers because oil is made up of carbon-hydrogen bonds and it is nonpolar, and water is polar. So they won't tend to mix in each other. However, if you took the pentane, that's the oil-based type substance, and you tried to dissolve it in another oil-based substance, it would dissolve. All right, so that brings us to, if we're talking about dissolving, another type of intermolecular attraction that occurs when you are trying to dissolve an ionic compound in water. So an ionic compound, like table salt, for example, When you put it in water, hopefully you remember that the first thing that happens if it dissolves is that the ions separate. So you have the cations and anions are separate from one another. They actually become what we call solvated by the solvent, which is water. And that simply means that the solvent molecules form a cage around the ions to stabilize them. And so this is called an ion and then dipole attraction. So it turns out that ion dipole attractions are actually stronger than hydrogen bonding, okay, which of course are stronger than dipole-dipole, which are stronger than London dispersion. So there's the ordering of intermolecular strengths of attraction. And here is a summary slide of all of them, which I think is great. So make sure that you can identify salvation. Notice that when we're talking about the cation, part of the ionic compound, that the part of water molecule that lines up to the cation is the partial negative end, which means the oxygen. Okay, so notice that all the oxygen atoms are closest to the cation. Now, if you had the anion being solvated, the hydrogens on water would be closest because they have the partial positive charge, and of course, opposite charges attract. And pay attention again how the water molecules align with each other for hydrogen bonding. This is another typical type question you could be asked on an exam about intermolecular forces. And this question is asking, which of the following has more than simply London dispersion forces? So you just have to look at them one at a time. If something is nonpolar, if a substance is nonpolar, it's only going to have London dispersion. So you have to look at every atom or molecule separately. So krypton, for example, any atom that is just an atom is only going to have London dispersion, okay? You can't have a dipole-dipole with just one atom. I'm hoping you remembered that carbon-hydrogen containing compounds are always nonpolar, as long as it only has carbon and hydrogen, so it only has London dispersion. Ammonia, if you drew the correct Lewis dot structure and shape, you would realize it is not planar, okay? It is trigonal bipyramidal. Therefore, it has the net dipole moment toward the nitrogen and lone pairs. So that has hydrogen bonding, dipole-dipole, and London dispersion, okay? So C is one of the correct answers. Aluminum chloride, you might just at glance looking at the formula think that it's ionic, and I don't really want to dispute that at this point, but suffice it to say, if it were truly pure ionic, it wouldn't be shown here with covalent bonds, but we're not going to worry about that. In any case, these are quite polar, and however, the dipoles all cancel each other. Okay, this is a symmetric planar molecule, so overall, that is nonpolar and only has London dispersion forces. Now, if it were treated as an ionic compound, it would, when put in water, completely separate into the cation and anion, and that would make ion dipole. Okay. CBr4, that is a tetrahedral, and although it has polar bonds, tetrahedrals are symmetric, and therefore the dipoles all cancel out with each other, and so overall, again, that's a nonpolar molecule and it only has London dispersion. So the correct answer is ammonia. All right, so there are several properties that are affected by the strength of the intermolecular force. We've talked about melting point and boiling point go up as the forces go up. Surface tension. That is when liquids get kind of a film on their surface. You may have played that little game with water before where it can you can float a paper clip or something on the surface. That is due to surface tension, and that occurs with liquids that have very strong intermolecular forces. And so if you were to look at a bunch of water molecules on a molecular level, you would see them all arranged, you know, so that the partial negative dipoles lined up with the partial positives. And because of that, you kind of think of the water molecules as all holding hands with each other and making kind of a barrier on the surface so no intruders can get in. So again, the stronger the attraction, the stronger the surface tension. Viscosity is, it's defined as resistance to flow. So honey is viscous, maple syrup is viscous, and it's because of the strength of the intermolecular attraction between the molecules. And typically things that are viscous have OH groups and hydrogen bonding. And we just talked about solubility and how that can be affected by the type of intermolecular force. And that, just remember, like dissolves like for that. All right, so we've talked about melting and boiling points and talked about as you add thermal energy, as you heat something up, you're going to loosen the intermolecular attractions. And also, hopefully you remember that temperature is actually a measure of kinetic energy, okay? So the higher the temperature of something, the more kinetic energy that substance has. And kinetic energy is energy of movement. So you imagine as you're heating up a container of water, you're loosening those intermolecular forces, and you're also giving the particles more and more kinetic energy. And so what happens when it boils is the particles finally get enough kinetic energy to escape the attraction they have with the other molecules. And that's when boiling happens. So this slide is really just a summary of what we've been talking about, but make sure you have a conceptual grasp on all of these and can explain them briefly. Here's a diagram of surface tension. So again, if you imagine that these are water molecules. Now, if you put if you just wax your car and then you splash some water on it, it's going to bead up. And that's because water likes itself much more than it likes a wax, for example, that is nonpolar, made of carbon-hydrogen bonds, or the air. And so it's going to make this little spherical shape. That's the best shape it can make to try to associate with itself and not other substances that it's not as strongly attracted to. Give you an idea of viscosity. These are the things that come out of, we refine oil, and then, I don't know if you've heard of fracking, but oil is made up of hydrocarbons, but they're of all different molar masses, and those are separated. Some are used for gasoline, some are used for natural gas, some are used for oil. But anyway, I want you to notice here that as the molar mass increases, the strength of the London dispersion force also increases, and then look what happens with viscosity, how thick they are, how gooey they are to us. That goes up as the strength of the intermolecular force goes up. And finally, capillary action. I'm sure you've probably experienced that, haven't you? You take a little glass tube and you stick it in a container of liquid without you having to suck on it or anything. You are going to see that liquid, typically, if it's water-based, being drawn up into the tube on its own. And that's because of a very strong attraction between the liquid and the glass surface. And again, we see that very often in water. We know that water is polar, right? And glass actually has polar bonds, the silicon-oxygen bonds. And so they both have polar bonds, and so they work up an attraction, and that's why you get the capillary effect. That's also why you see a meniscus, that curved surface, anytime you have water in any type of tube container. That is it for intermolecular forces.